There are only 9 objects known to humankind that have crossed, or will ever cross, the boundary between the solar system and interstellar space. Remarkably, while some are of extraterrestrial origin, most were crafted by human hands. For years, celestial bodies from beyond our solar system have captivated astronomers and the public alike. At Harvard University, researchers Avi Loeb and Shokruz Kakarov are piecing together this interstellar puzzle. Armed with a sophisticated program called GalPot, they are doing something unprecedented, rewinding the cosmic clock to trace these objects back to their origins. But their investigation doesn't stop there. Loeb and Kakarov have also charted the paths of human-made probes, projecting the course of these emissaries into deep space, estimating when they'll reach the other side of the Milky Way, and exploring if and when they might, one day, come close to our solar neighborhood again. However, one extraterrestrial interstellar object and one human-made probe currently on a trajectory to exit the solar system were not included in the study. Stay tuned to discover which objects made the list and which ones haven't.
In today's episode, we are discussing an intriguing paper titled Galactic Orbits of Interstellar Objects, authored by Shokruz Kakarov and Abraham Loeb. This study explores the enigmatic journeys of interstellar travelers, blending science with a touch of cosmic mystery. While we aim to stay faithful to the main findings of the paper, we'll also take some fascinating detours to explore the nature and history of these remarkable objects. For those interested in reading the full paper, we have included a link in the description below. Please like the video, if you do, and consider subscribing for more content like this.
In recent years, the discovery of extraterrestrial interstellar objects like Oumuamua and Comet Borisov has fueled immense curiosity about where these mysterious travelers come from and what forces set them on their journeys. One of the big questions scientists grapple with is pinpointing the origin of each of these objects. If we could identify their likely sources, we might gain valuable insights into their nature and the events that created them. In this paper, the researchers tackled this challenge by retracing the paths of 3 interstellar objects that entered our solar system, mapping their trajectories within the Milky Way's gravitational field. Their goal was to connect these cosmic visitors to potential stellar populations. For simplicity, they set aside transient gravitational structures like spiral arms and the galactic bar, a reasonable approximation when studying orbits in the outer regions of the galactic disk. By winding the clock backward and following the orbits of these objects, the team was able to identify the regions within the Milky Way that could be their potential birthplaces, offering clues about the broader galactic environments they once called home. An interesting aspect of their research was using the relationship between a star's scale height in the Milky Way disk and its age. Simply put, older stars and objects tend to move farther from the disk's midplane over time. The researchers applied this concept to the 3 interstellar objects, analyzing how far each one strayed vertically from the midplane to estimate their probable age. Stars and interstellar objects move through an extremely diffuse and sparse environment with vast distances between them, so direct physical collisions that might alter their motion are rare. Instead, their paths are shaped by the gravitational influence of surrounding objects, particularly massive ones like galaxies and star clusters. This means that both stars and interstellar objects react in the same way to these gravitational forces. This is important because it allows scientists to study the vertical position of an interstellar object in the Milky Way and use that information to estimate how old that object is. So, no matter how far an interstellar object has traveled, its position in the Milky Way can reveal clues about its age and history. The authors applied similar techniques to predict the future paths through the Milky Way of 4 iconic NASA probes launched decades ago. To determine the galactic paths of interstellar objects, researchers utilized GalPot, a specialized tool that maps gravitational potential and tracks orbital paths within a galaxy model based on symmetry around the central axis. Simply put, GalPot functions as a simulation engine that enables astronomers and astrophysicists to model gravitational dynamics throughout various regions of a galaxy, helping them understand how objects navigate this gravitational field over time. Standing for galaxy potential, GalPot relies on a mathematical model to simulate gravitational forces across the galaxy's main components, the central bulge, disk, and halo. For example, in the Milky Way, gravity is strongest near the dense center, where a supermassive black hole is located but extends outward through the disk and into the halo, which is less dense. GalPot accounts for these variations, offering a realistic picture of how objects might move within a galaxy. By entering the initial position and speed of an object, GalPot computes the gravitational forces acting on it, allowing scientists to predict both its past and future locations. Oumuamua was the first confirmed extraterrestrial interstellar object detected passing through our cosmic neighborhood. Discovered by the Pan-STARRS telescope in Hawaii on October 19, 2017, its name fittingly means "a messenger from afar arriving first" in Hawaiian. It was initially estimated to have a cigar-like shape, but later models suggested it might be more flattened, resembling a pancake or disc. As scientists tracked its path, they noticed Oumuamua was exhibiting slight accelerations that couldn't be explained by gravitational forces alone. In typical comets, such behavior is due to outgassing, the release of gases that can act like a natural rocket engine. Yet, despite this acceleration, no coma or tail was visible around the object. It seemed to be acting like a comet, but didn't look like one. This unusual behavior sparked various theories. Some suggested that it was outgassing unfamiliar substances or that it was composed of exotic ices, while others speculated it might even be an artificial object, possibly an alien probe or piece of extraterrestrial technology. Its reddish surface resembled objects in the outer solar system, likely altered by exposure to cosmic rays over millions of years. Unfortunately, the opportunity to study Oumuamua was brief. Traveling at high speed and on a trajectory that took it swiftly out of our reach, it faded from view almost as quickly as it appeared. The data collected during its short visit has been analyzed extensively, but many questions remain unanswered. Oumuamua's passage through our solar system was a watershed moment in astronomy. It not only opened our eyes to the existence of interstellar objects visiting our celestial neighborhood, but also highlighted how much we have yet to learn about the universe beyond our solar system. Its mysterious nature continues to inspire scientific inquiry and the search for other interstellar visitors that might help unravel the secrets it left behind. The research team calculated that the separation between Oumuamua and the Sun follows a period of about every 2.2 billion years, with the object being on the other side of the Milky Way disk, relative to the Sun, approximately 1.1 billion years ago. They estimated Oumuamua to be much younger than the other 2 extraterrestrial interstellar objects studied, with a likely age of 1 to 2 billion years. Comet Borisov, the second confirmed interstellar object to enter our solar system, was discovered by amateur astronomer Gennady Borisov on August 30, 2019. Moving at an incredible 32 kilometers per second relative to the Sun, its hyperbolic trajectory revealed it was not bound by our star's gravity. What made Borisov remarkable was its potential to reveal the composition of materials from other star systems. While it contained elements like cyanide, common in comets from our Oort cloud, it also differed in significant ways. Borisov was unusually low in water, but rich in carbon monoxide, far beyond what's typical in local comets. This suggested it may have formed in an exceptionally cold region, possibly on the outer edges of a distant star system. As it neared the Sun, Borisov displayed a bright dust halo and active jets, offering scientists a rare look at how interstellar comets react to solar radiation. Observing Borisov was a race against time, as its high speed and open-ended path meant it would soon depart, leaving only a brief window to gather data. Borisov's visit holds profound implications. Its similarities to local comets hint that the fundamental building blocks of planets, and perhaps life, might be common throughout the galaxy. At the same time, its unique traits, such as the high carbon monoxide levels, challenge existing theories on comet formation and composition. Researchers Kakarov and Loeb calculated that Borisov's separation from the Sun varies on a cycle of approximately 3.2 billion years. Around 1.6 billion years ago, Borisov was on the opposite side of the Milky Way from the Sun. They also found that its galactic path mirrors that of the Sun, suggesting a similar age of about 4.6 billion years. In 2014, a bright fireball blazed through the skies near Papua New Guinea, seemingly a meteor event not unlike many others witnessed around the world. 5 years later, Harvard researchers Amir Siraj and Abraham Loeb identified it as a potential interstellar object, Interstellar Meteor 1, or IM-1. While not all astronomers agree with this claim, the US Department of Defense confirmed it independently in 2022. What makes IM-1 truly remarkable is its speed and composition. Prior to entering the solar system, IM-1 was moving at a speed of 60 kilometers per second relative to the local standard of rest of the Milky Way galaxy, faster than 95% of all stars in the vicinity of the Sun. Unlike Oumuamua, which was observed from afar, IM-1 interacted directly with Earth's atmosphere, displaying extraordinary strength as it burned up. It disintegrated at pressures more than 20 times higher than those typical for stony meteorites, and even twice as high as iron meteorites. Perhaps most intriguingly, some scientists theorize that IM-1 may have originated from a supernova explosion. Supernovae have been observed to produce iron-rich bullets that could potentially explain IM-1's high metallic content and unusual strength. In 2023, the Galileo project organized an expedition to the Pacific Ocean near Papua New Guinea to search for fragments of IM-1. The effort was funded by cryptocurrency entrepreneur Charles Hoskinson and led by Avi Loeb. The team used a magnetic sled to search the ocean floor along IM-1's projected path, where they found several hundred tiny, spherical iron fragments. They believe that at least 50 of them are likely from IM-1. The expedition's findings and claims remain controversial, with ongoing debate in the scientific community about the true origin and significance of the recovered remnants. Kakarov and Loeb found that separation between IM-1 and the Sun follows a period of around 4.3 billion years, and a significantly greater vertical movement than the Sun, likely originating from an older region of the Milky Way. On March 9, 2017, a remarkable event lit up the skies over the Atlantic near Portugal. A brilliant, fiery object streaked through Earth's atmosphere, breaking apart at around 23 kilometers altitude. This object, potentially our second known interstellar meteor, was dubbed Interstellar Meteor 2, or IM2. IM2 was about 1 meter across and nearly 10 times more massive than its predecessor, IM1. It raced toward Earth at 40 kilometers per second, or 144,000 kilometers per hour. This extraordinary speed hints at its possible interstellar origin. IM2's strength was equally astonishing. As it disintegrated, scientists found it was unusually tough, ranking third out of 273 fireballs in NASA's Near-Earth Object Catalog in terms of material strength. IM2 withstood pressures about 20 times higher than typical stony meteorites and twice as high as iron meteorites, suggesting it may be fundamentally different from objects in our solar system. The discovery of IM2 so soon after IM1 raises questions about the nature of interstellar objects. If these two meteors are part of a larger population, it could mean a substantial portion, perhaps 40%, of the galaxy's heavy elements is locked in meter-sized objects drifting through interstellar space. This unexpected abundance suggests an origin story beyond typical planetary ejections, hinting at connections to supernovae. Kakarov and Loeb did not include IM2 in their study. These 4 extraterrestrial interstellar objects serve as cosmic time capsules from different eras, each providing a glimpse into various stages of our galaxy's formation. Building on their work, the researchers expanded the study to include 4 human-made spacecraft currently on interstellar trajectories. They mapped each probe's path through the Milky Way, estimated when they might reach the far side of the galaxy, and considered the possibility of a future return to our solar neighborhood. In the next segment, we'll explore their findings and take a closer look at the fascinating missions and histories of these interstellar probes. Launched on September 5, 1977, Voyager 1 set out on a mission that would ultimately surpass its initial objectives. Voyager 1's journey began with a close flyby of Jupiter in 1979, coming within 349,000 kilometers of the gas giant. This encounter provided a gravitational boost, accelerating the spacecraft and redirecting it towards Saturn. While near Jupiter, Voyager 1 studied the planet's atmosphere, magnetic fields, rings, and captured detailed images of 5 of its moons. In 1980, Voyager 1 reached Saturn, passing within 124,000 kilometers of the ringed planet. Its instruments analyzed Saturn's atmosphere and rings, offering humanity the first close-up views of Saturn's moons, including Titan. The gravitational pull from Saturn ultimately directed Voyager 1 out of the ecliptic plane, concluding its planetary exploration phase. Voyager 1's most remarkable achievement came years later. On August 25, 2012, it became the first human-made object to enter interstellar space, crossing the heliopause at around 121 astronomical units from the Sun. This historic milestone made Voyager 1 the farthest human-made object from Earth. As of October 2024, it was about 165 astronomical units, or approximately 25 billion kilometers from our planet. Despite this vast distance, Voyager 1 continues to transmit data back to Earth through the Deep Space Network, though signals now take nearly a day each way. The spacecraft's endurance is a feat of engineering, powered by radioisotope thermoelectric generators, RTGs, that convert the heat from radioactive decay into electricity. Voyager 1 has operated well beyond its expected lifespan. Perhaps one of Voyager 1's most fascinating aspects is its golden record. a gold-plated audio-visual disc designed as a message to potential extraterrestrial discoverers. Curated by a team led by Carl Sagan and Timothy Ferris, the record includes images of Earth, scientific information, sounds of nature, greetings in 55 languages, and music from around the world, showcasing the diversity of life and culture on Earth and reflecting humanity's desire to connect with the cosmos. Voyager 1 is expected to reach the theorized Oort cloud in about 300 years and may take around 30,000 years to pass through it. According to Kakarov and Loeb, the distance between Voyager 1 and the Sun oscillates over a period of 3.6 billion years, with Voyager 1 predicted to reach the far side of the Milky Way's disk relative to the Sun in approximately 1.8 billion years. Voyager 2, the twin to Voyager 1, has charted a path through the solar system that is uniquely its own. Launched just a few weeks before its sibling in 1977, Voyager 2 embarked on a remarkable journey, becoming the only spacecraft to visit Uranus and Neptune, the ice giants of our solar system. The mission of Voyager 2 was ambitious. Using a rare planetary alignment, it conducted flybys of Jupiter, Saturn, Uranus, and Neptune, leveraging gravitational assists to propel itself from one planet to the next. This grand tour provided humanity with close-up views of these distant worlds and their moons. At Uranus, Voyager 2 discovered 10 new moons and examined the planet's bizarre magnetic field, which is significantly tilted relative to its axis of rotation. An 11th moon, Perdita, was discovered later in archival images. The spacecraft revealed Uranus's faint ring system and provided insights into its atmosphere, which appeared surprisingly featureless compared to other gas giants. The flyby of Neptune was equally groundbreaking. Voyager 2 discovered 6 new moons and observed the planet's Great Dark Spot, a massive storm comparable to Jupiter's Great Red Spot. Perhaps most intriguing was the discovery of active geysers on Triton, Neptune's largest moon, spewing nitrogen gas into space. These findings revolutionized our understanding of the outer planets and their satellites. After completing its planetary encounters, Voyager 2 continued its voyage toward interstellar space. In November 2018, it joined Voyager 1 in crossing the heliopause, providing a second set of measurements from a different location. This allowed scientists to compare data and gain a more comprehensive understanding of the heliosphere's structure and its interaction with the interstellar medium. Voyager 2 also carries a golden record, mirroring the one aboard Voyager 1. Over the years, the spacecraft has faced challenges typical of such a long mission. In 2011, engineers performed a thruster swap maneuver, switching to backup thrusters to conserve power and extend Voyager 2's operational life. More recently, in July 2023, NASA temporarily lost contact with the spacecraft due to a misalignment of its antenna. The team managed to re-establish communication, demonstrating the resilience and ingenuity behind the mission's operations. Voyager 2 continues to send back data, contributing to our understanding of cosmic rays, magnetic fields, and the nature of interstellar space. Each bit of information helps piece together the vast puzzle of our galaxy. As Voyager 1 and 2 continue their journeys into the unknown, they serve as a reminder of our place in the cosmos. They have shown us the stunning diversity of our solar system and given us our first taste of truly interstellar exploration. The authors found that the separation between Voyager 2 and the Sun follows an extraordinarily long period, about 13 billion years, in other words, comparable to the age of the universe. The probe is expected to reach the other side of the Milky Way disk relative to the Sun in about 6.5 billion years. Even more interesting, the spacecraft is predicted to come within about 325 light-years of the Sun on its first return. Pioneer 10, launched on March 3, 1972, was a groundbreaking mission in space exploration. It became the first spacecraft to traverse the asteroid belt and make direct observations of Jupiter, opening new frontiers in the outer solar system. Passing through the asteroid belt posed unique challenges, as scientists were concerned about potential collisions with space debris. Pioneer 10's successful journey proved that such missions were viable, clearing the path for future exploration. On December 3, 1973, Pioneer 10 flew by Jupiter's moons, Callisto, Ganymede, Europa, and Io, and the next day reached its closest approach to Jupiter at 200,000 kilometers. Its instruments captured invaluable data on Jupiter's atmosphere, magnetic field, and radiation belts, and took the first close-up images of the Great Red Spot. The spacecraft's findings on Jupiter's intense radiation belts provided essential insights that would guide the design of future missions. Following its encounter with Jupiter, Pioneer 10 continued its journey, became the first human-made object to cross Neptune's orbit on June 13, 1983, and achieved escape velocity from the solar system. Although its official mission ended in 1997, it transmitted data until 2003, when it was about 80 astronomical units from the Sun, and its power source finally waned. Pioneer 10 now silently drifts toward the star Aldebaran in Taurus, a journey that will take over 2 million years. The spacecraft also carries a gold-anodized aluminum plate etched with symbols designed by Carl Sagan and Frank Drake. The iconic plaque includes illustrations of a man and a woman, Pioneer 10's trajectory, and a schematic of the solar system's position in the galaxy, serving as a message to any extraterrestrial life that might encounter it. The two Harvard researchers determined that the spacecraft's distance from the Sun follows a period of about 4.6 billion years, with Pioneer 10 reaching the opposite side of the Milky Way's disk relative to the Sun in approximately 2.3 billion years. Launched in 1973, just a year after its predecessor, Pioneer 11 set its sights on two of the solar system's giants, Jupiter and Saturn. After a successful flyby of Jupiter in 1974, where it gathered critical data and stunning images, Pioneer 11 used the planet's immense gravity to slingshot itself towards Saturn. This maneuver was a remarkable feat of navigation and planning, showcasing the precision required in interplanetary travel. Pioneer 11 became the first spacecraft to reach Saturn, arriving in 1979. It provided humanity's inaugural close-up images of the ringed planet, unveiling details that were previously unseen. The spacecraft discovered two new rings, thin and faint, adding to the complexity of Saturn's already intricate ring system. It also identified new moons, expanding our knowledge of Saturn's entourage of satellites. The data collected on Saturn's magnetic field, radiation belts, and atmospheric conditions were invaluable. Communication with the spacecraft was maintained until 1995, when power constraints and the increasing distance made it impractical to continue. The last signal received marked the end of an era, but the spacecraft continues its silent journey through space. The spacecraft's navigational achievements were particularly noteworthy. Precise calculations and control were necessary to achieve the gravity assists that propelled Pioneer 11 from Jupiter to Saturn and then out of the solar system. These maneuvers paved the way for future missions that would rely on similar techniques. Pioneer 11 also carries a gold anodized aluminum plate, identical to the one on Pioneer 10, designed to communicate the story of humanity to any extraterrestrial intelligence. Pioneer 10 and 11 are no longer active, but they stand a testament to the early days of space exploration when bold ideas and daring missions expanded the horizons of what was possible. They have fallen silent, but their legacy endures, inspiring future generations to look to the stars and wonder what lies beyond. The paper's authors determined that the distance between Pioneer 11 and the Sun follows a cycle of approximately 5 billion years. They project that the probe will reach the opposite side of the Milky Way disk, relative to the Sun, in roughly 2.5 billion years. In the realm of space exploration, few missions have captured the imagination quite like New Horizons. Launched in 2006, this spacecraft embarked on a voyage to explore Pluto and beyond. The journey to Pluto was not a straightforward shot. To conserve fuel and further accelerate the spacecraft, mission planners designed a trajectory that took New Horizons past Jupiter. This gravity assist maneuver boosted New Horizons' speed to an astonishing 52,000 miles per hour, making it the fastest human-made object to ever travel through our solar system, and allowing it to reach the dwarf planet in 9 years. On July 14, 2015, New Horizons made its historic flyby of Pluto, passing within just 7,800 miles of its surface. This close encounter revealed Pluto to be a complex world with a surprising variety of landscapes. The spacecraft's cameras captured images of vast plains of nitrogen ice and mountains of water ice as tall as the Rockies. These discoveries transformed Pluto from a distant, fuzzy blob into a dynamic, geologically active world. But New Horizons didn't stop at Pluto. In 2019, it ventured even deeper into the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. One of the most intriguing recent findings from New Horizons is evidence for what might be a second Kuiper Belt. As the spacecraft continues its outward journey, it is detecting more dust impacts than expected, suggesting the presence of a previously unknown population of objects beyond the known Kuiper Belt. This discovery could reshape our understanding of the solar system's structure and evolution. New Horizons is still going strong, its nuclear power source allowing it to operate for decades to come. Eventually, the spacecraft is expected to reach the heliopause, thus allowing for direct comparisons with data from the Voyager probes. Kakarov and Loeb did not include New Horizons in their study. While this study brings fascinating insights, it's still limited by the accuracy of the model used. GalPot offers a robust foundation, but it doesn't fully capture the complexities of our galaxy. The Milky Way is far from static. It's a dynamic, constantly evolving system. Features like spiral arms, molecular clouds, and dark matter all interact with interstellar objects, making these paths closer to approximations than precise routes. Yet, as we gather more data and refine our models, these predictions will become increasingly accurate. The exploration of interstellar objects is only beginning. Advanced observatories like the Vera Rubin Observatory on the near horizon will help us detect even more of these elusive visitors. Understanding their compositions will be equally valuable. Looking forward, it's awe-inspiring to consider our human-made probes on their own cosmic journeys. It's humbling to imagine that, perhaps billions of years from now, one of our probes could encounter another civilization, becoming a message in a bottle from a civilization long past. Ours. This research also lays the groundwork for future exploration. With larger and more sensitive observatories, we may detect more interstellar travelers, each with its own story to tell. Finally, this study underscores the powerful role of computational models and simulations in modern astrophysics. Through sophisticated modeling of the galaxy's gravitational field, astronomers can unravel cosmic journeys that would otherwise be lost to time.
Thank you for joining us on this interstellar voyage. Share your thoughts in the comments, and if you enjoyed today's episode, be sure to like, subscribe, and check out the paper linked below.